So next up, we're gonna have Daniel, who is a PhD student at the UVA and the VU, and he's working on knowledge graphs. And I like it because I think it's a bit of a different angle on a lot of the problems we're talking about. So I'm really looking forward to what he has to say about how we find entities and relationships in data. So please.
Okay. Thanks, Sergi. Thanks everyone for coming, and also thanks to the organizers for inviting me today. So yeah, today I'm going to talk about some recent work that together with my supervisors, we recently presented at the web conference. So this is work on learning representations of entities in a knowledge graph based on their textual description. So a graph, as some of you might already know, is a data structure that has nodes and then a set of edges that denote some sort of relation between these nodes. And in particular, a knowledge graph is, well, a graph that has some sort of domain knowledge attached to it. And here we have an example of a knowledge graph that talks about a number of countries and cities and the way they are related between each other. And this is an example application, but we can also use these graphs to store other types of information like biomedical data. These knowledge graphs are also used in the retail industry and also in social networks. So yeah, an important aspect about knowledge graphs is the fact that they are dynamic. Just because, well, the world is dynamic, and if we have a knowledge graph about the world, this graph is bound to be incomplete. And this is an example, this is a visualization of a very popular knowledge graph called Wikidata that has millions of entities. And even though there's a lot of people contributing to this graph, um, it's still updated all the time, which means that this is a data structure that is noisy, it's constantly changing. So we need methods to deal with this fact. Um, so this motivates the application of machine learning to this method. And using machine learning will allow us to do things like clustering, node classification, and link prediction, which is one of the main tasks that we'll look at in this work. So one way to do link prediction in knowledge graph is to use knowledge graph embeddings. So just to illustrate this idea, here we have a small knowledge graph with a couple of cities from the Netherlands. So we have Amsterdam and Utrecht and the Netherlands, and then flowers. Uh, so knowledge graph embeddings are basically vector representations of entities and relation types. So some of you might already be familiar with word embeddings, for instance. In this case, we have vector representations of entities and relation types. And the idea is that these vectors will lie in some high dimensional space of an arbitrary dimension. Usually, this can be hundreds of dimensions. But let's assume we have just 2 dimensions. And here we're visualizing the way these embeddings are supposed to behave. So we have the knowledge graph is telling us that Amsterdam and the Netherlands are related via relation R1. So we would like their vector representations to reflect this information in some form. And in this case, that form is basically a translation in the embedding space. So this is a very quick summary of how knowledge graphs work. And the basic algorithm is we start with by initializing randomly embeddings for every entity and every relation type in the knowledge graph. And then we run basically gradient descent so that we gradually optimize these embeddings so that they reflect the information that is present in the graph. And once we're done with this process, we now can do things like link prediction, because now we can take, for instance, the vector for Amsterdam, and we can add the vector R2. And then we basically add these vectors and look at the resulting vector and look at what entities are in the neighborhood. And this is essentially how we can do link prediction with knowledge graph embeddings. So let's assume we run this process, we have our embeddings, but then a new entity appears. So now we have Harlem here. And the issue here is that, well, we just finished our optimization algorithm and Harlem appear, which means we don't have an embedding for it. Uh, and this means that then we cannot do any predictions involving this new entity. This is a problem because running these algorithms is not cheap. So ideally, we would like to have methods that deal with this sort of phenomenon, particularly for knowledge graphs, since we know that they are constantly changing. So we call this a scenario where a new entity appears, the inductive scenario. So we would like our methods to generalize to things that were not during training. And the idea here is to use information that is additionally available in knowledge graphs, in this case, textual description. So here again, we have our two entities, Amsterdam and the Netherlands. So we have textual descriptions for them that are taken from Wikipedia. And the idea is, instead of assigning a separate vector, a separate embedding to every entity in the knowledge graph, we're going to make these embeddings a function of their textual description. So we're going to use an encoder to map these descriptions to a vector. And then we proceed as before, we just optimize with gradient descent so that the embeddings reflect the information in the knowledge graph. So we call this method BLP, which is short for BERT, for link prediction. And well, the reason is that the encoder is essentially a transformer-based encoder initialized with BERT, courtesy of Hugging Face. And basically, now this will allow us to do a link prediction using the textual descriptions of entities. Okay, so the way we evaluate this for link prediction involving new entities is to consider two scenarios. So we have first a knowledge graph from which we remove a set of entities, and then we train our system using the graph, and then at test time, we predict links between the original graph and entities that were removed. And here we compare with other methods that you could consider for embedding entities based on their description. So a simple model is just a bag of words where we average embeddings. We also have a CNN encoder that it seems to be prone to overfitting. And then we have BLP in this case. And these metrics that we consider here are essentially link prediction metrics, where higher is better. And here we observe that BLP allows us to work on this scenario where new entities appear and then we need to make a prediction for them. So this is the first scenario. And the second one, we call it the transfer scenario. So in this case, we take the knowledge graph and then we again remove entities from it, train with the original graph, and then at test time, we only predict between all the pairs of entities that were removed. So this is similar to training on a large knowledge graph and then transferring to a separate graph. And again, here we have similar baselines, and also we have BERT plus KG, which is essentially BERT as a language model, but trained with an additional link prediction objective. And the hypothesis for this model was that having this combined objective between language modeling and link prediction would result in better representations, whereas BLP is specialized in the link prediction case. And again, we observe here that BLP is a very effective method for this scenario as well. So now that we're done with the link prediction task, we look at the encoder and we see, okay, we have this encoder that is able to take as input the description and produce a vector representation. Can we do something different? So the first thing we do is to look at entity classification. So we reuse the encoders that we trained for link prediction as feature extractors for a classifier that has to determine the type of an entity. And here the metric that we evaluate is accuracy, basically. And we again compare with the same encoders than before, but also with sentence word. And again, we notice that BLP, in this case, since it's a model that is specialized for descriptions of entities, is able to compress the information about an entity in a way that is useful for a classifier. And also, importantly here, we have to notice that we do not optimize the encoder for this task. We only use it as a feature extractor, but we only optimize the classifier. Okay, and the third task is information retrieval, which has been mentioned a lot today. Um, the task here, again, is basically given a query, retrieve a set of relevant documents. And here we wanted to see if we could reuse the encoder for link prediction also for the information retrieval task. So we use it to encode on one hand the query, and on the other hand a set of documents, and then we compute a score between all the vector representations. And the approach is to start with BM25 just to get a set of relevant documents, and then re-rank the documents according to their scores. Also, I should mention again that here in this case, we're not optimizing the encoder for the task. We're interested in looking at how these representations after link prediction are useful for information retrieval. So there's not really any gradient descent going on here. So in the data set that we evaluate, it's basically a data set for entity-oriented search. And there is a number of different queries that we considered. So here on the left, we have keyword-based queries like bicycle, holiday, nature. And as you can see in this case, this is a query that is very different from the type of text that the encoder for link prediction was trained for. So it's natural to see that in this case, there are not really significant improvements over the BM25 baseline. But then when we move to queries that look more like well-formed questions, then we did observe significant improvements over BM25. So this is an interesting result because even though the model was not trained for question answering or information retrieval based on queries, it's learning to map descriptions of entities and questions about them to vectors that are similar. So yeah, this is just a couple of examples to give you an idea. We have two queries. So on the top, there is who founded Intel, and then a list of all American inventions. And we see that as expected, BM25 is relying a lot on the surface form. Whereas after introducing BLP, we get more semantically related results. Okay, yeah, so in summary, with this work, we observed that it's possible to do link prediction over a knowledge graph, even if you have entities that were not seen during training, as long as you have a textual description for them. And also that these representations are useful for tasks like classification and information retrieval without being explicitly fine-tuned for them, at least for the information retrieval task. And yeah, I think this work has potential for improvements. For instance, in a knowledge graph, not only new entities can be added, also new relation types. So can we extend this framework to that case? And also, as Andrew mentioned, there's a lot of work on building or designing more efficient encoders. In this case, we used BERT, which can get a bit expensive, especially for long descriptions. But of course, we can also incorporate advancements in making these encoders more efficient. So that's my talk. If you want to play with these ideas, all the code is available. And thanks. I'll take any questions.
Thank you very much, Stan. I think it's really nice work bridging the gap between knowledge bases and machine learning. So do we have questions? No hands raised? Okay, I see one.
Hey, great presentation, thanks. I'm curious, what is the requirement for this kind of work? Does it only work on Wikipedia kind of content where you have already annotated entities, the relationship between the entities, and so on? Or does it also work like what is the basic given thing for this model to reuse for non-Wikipedia data, for example?
Right. So the information that you need to apply this to another domain is just a knowledge graph and also textual descriptions of the entities in your knowledge graph. So at first, I think the most difficult part to acquire is the knowledge graph. If you're in a very specialized domain, this is a very labor-intensive task. But textual descriptions you can easily obtain, for instance, from Wikipedia. If I mean, Wikipedia has a lot of coverage. That would be one way to start, I think.
Questions?
What does knowledge graph or how come that knowledge graphs care about Euclidean distance, in a sense that, well, it's already like you have this assumption when you do for example MSc between embeddings, or you do cosine distance dot product, you assume that Euclidean distance applies to very high dimensions. But now it goes a little bit further. So now it's not only about like that concept that what is the shortest distance between 2 points, but now it's also a concept that what is the shortest distance between 2 points passing by that other point. So it becomes even more, I guess, abstract, but I don't really know how to answer this question.
Okay, so I guess the question is whether these embeddings are good at, well, embedding the structure of the graph, at least in a Euclidean space. Yeah, so in this work, the sort of embeddings, or one of the type of embeddings that we consider, indeed treats entities as embeddings in a Euclidean space, but that's just one variant, and there is a lot of work on how or what are suitable representations for graphs that is orthogonal to this work. So we can also represent entities as complex vectors, for instance, or also as vectors in a hyperbolic space, which is really good at modeling hierarchies. And that's also another way of extending this work. So can we, instead of making BERT produce BERT vectors that lie in a Euclidean space, can we use it for vectors in a hyperbolic space, for instance?
So a couple of other hands.
Yes, thanks for the talk. So you mentioned in the end, you could extend this towards unseen relations. And I was already like brainstorming on what would be like, would there be a possibility to use the description of a relationship actually to do the same trick?
Yeah, I think that would be one way to go. So essentially extend the same approach to relation types. So again, you can also obtain descriptions for relations from Wikipedia, or also Wikidata has descriptions for relations. So it would be one way to extend this.
One last one.
Do you have any like intuition why the entity classification in this task works? Because you already have like BERT encoder, which is trained not for entity classification task. Because you showed that the knowledge graph objective works for entity classification just too well, and that's quite unusual.
Yeah, so sorry, I don't understand. So you mean
like just the you use the straight BERT, it's frozen BERT encoder, and apply that for entity classification.
Yeah.
And why does the knowledge graph objective work in that case?
Okay. Yeah, I think, for instance, if you look at sentence BERT, it's only looking at the graph, whereas we're using this other model that has an additional input from the knowledge graph that tells it a lot about how entities are related, which ones are similar in a particular context in the knowledge graph, and that acts as extra data that is used to train this classifier.
Does it really just generalize well? Because it seems like out of the main text for the entity representation would not work either, because you just reduce the space which like initial BERT encoder just use it and to less space which used for this particular knowledge graph.
Yeah, I agree. And I think also generalization is a good point to make here. Also, something that I forgot to mention is that for this is not working. This is also not working. Okay. Yeah, so for the entity classification task, we wanted to stick with this idea of what happens with unseen entities. So this encoder was trained with a set of entities, and similarly, the classifier was trained only with the entities that the encoder saw during training. So at test time, the classifier is also seeing features that it didn't see during training.
Okay, thank you.
One last question.
Great research. And I wanted to ask if it's possible, maybe it's already have been done, to extend it to visual descriptions.
Wow.
As an
Like
image
as
encoder.
in captions, for instance?
Yeah, so just like Bird encodes description, have an image encoder.
Right.
So images of the entity.
Yeah, I think probably this is also related to multimodal knowledge graphs. So in this case, I mean, this is a very general framework. We have a knowledge graph where entities can have different attributes. And in this case, we decided to use textual descriptions. And to use that information, you need an encoder that is able to, well, encode that information. But we also have knowledge graphs where entities have an image. Wikidata is an example. So in that case, you would need a special encoder for the image, like a CNN-based encoder that you could potentially combine with a textual description.